Okay, this is the first lecture in this course, which is an introduction to analysis. And we're starting our introduction to analysis with an introduction to numbers. And I'm going to start out talking about the square root. And the way we have this discussion of the square root kind of sets up the way that a useful way to think about numbers as we go ahead. And we start off our classical examples of numbers. There's the natural numbers where you count like a child, 1, 2, 3, 4. From there we proceed to the integers where we include 0 as a concept of a number, as well as the negative numbers. Okay, and they were meant to be dots before the integers here, of course. And we have the rational numbers where we talk about fractions of things. And at the time of the Greeks, the rational numbers were the penultimate way of talking about numbers, the latest thing in how numbers could be talked about. But then they ran up against a number that this couldn't deal with in the time of the Pythagoreans. Okay, and here I'm sure you've heard about the Pythagorean theorem, where if you have a right triangle with legs A and B and a hypotenuse C, then A squared plus B squared is equal to C squared. Okay, and let's take the simplest case here where A and B are both equal to 1, and so we have that 1 squared, which is 1, plus itself is equal to 2. And so to get a value of C, we create a new name for this number, the square root of 2, but this doesn't turn out to be very useful, as we shall see. Okay, so you can't just call a number a name and have it do anything. You need to actually have it related to human relatable terms. And so in trying to figure out this, the Pythagoreans said, well, how can we represent this as a fraction? And so we'll say, all right, take the square root of 2, and let's see if we write it as p divided by q, where p and q are both integers. And let's be nice to ourselves. Let's reduce this number to lowest terms. What can we say about p and q? Well, first off, let's square both sides. And so then we get 2, which we do know what 2 is. It's equal to p squared over q squared, and we hate fractions, so we multiply both sides by q squared. Okay, and so 2 times q squared is equal to p squared. What does this mean for p? Well, first off, it means that p squared is even. Okay, and since p squared is even, that must mean that p was even too, because if p was odd, its square would be odd. And you can just write that down. I'll toss it out as a challenge for you to do it on your notes right here. Write down that if p is odd, its square must be odd. So, but in any case, we know that since p squared is even, that p must be even. All right, so if p is even, it's equal to 2 times n, and so p squared is 2 times n squared, so 2 times n squared is 4n squared. Okay, so 4n squared is equal to p squared, but p squared was equal to 2 times q squared. So I cancel out a 2 on each side of this equation, and that gives me that 2 times n squared is equal to q squared. And so this means, in the same way as we did before, since q squared is even, q has to be even. Okay? Now, we know that 2 divides p. That's what p being even means. We know that 2 divides q, which is what q being even means. But we had assumed that p and q had no common factors. That is, we'd assumed our fraction p over q was in lowest terms with all of the common factors canceled out. And so we have a contradiction here. If we cannot represent the square root of 2 exactly as a fraction. And so what can we do? Okay, because, all right, this is something that's basic. I mean, you can have a couple of boards a foot long, attached to each other at a right angle, and you can attach a board to that free side. How can we calculate, okay, how long the hypotenuse board is to be? Because this is something we have to figure it out. Well, we approximate it. You know, I put this in terms of carpentry. If you ever have done any cutting of boards, you know that you're going to have to allow yourself some leeway. Okay, and so let's start off. We're going to approximate the square root of 2. We'll start off by having a very crude approximation by saying that the square root of 2 is somewhere between 1 and 2. And I could do the mathematics on it. I'm going to just do it. Look at the picture. My goodness. It can't be any bigger than 2 because the length of these two sides are 2, and it can't be any less than 1 because the length of this one side is 2. It can be done that, but let's just be reasonable here. Okay, now going to set up something where we can get a better and better approximation of it. So let's suppose that we have square root of 2 is less than some number x. If we do that, I can divide both sides by x, and this tells me that 2 over the square root of x is less than 1. Now, what I can do here is say, hey, I've got this true right here. The square root of 2 is less than x, and then the square root of 2 less than over x is less than 1. What if I multiply the left-hand sides by the left-hand sides and the right-hand sides by the right-hand sides? This will give me that 2 over x is less than x. Now I multiply both sides of this inequality by x. That'll tell me that 2 is less than x squared. So I know that 1 is less than square root of x, which is less than square root of 2, which is less than 2, which is less than x squared. If I divide through everything here by x, then I have 1 over x is less than the square root of 2 over x is less than 2 over x is less than x. Okay, and so I can again multiply. Okay, I can note that 2 over x is equal to square root of 2 over x times the square root of 2. Square root of 2 over x is less than 1, and so this is less than this, and so therefore it's all less than the square root of 2, which itself was less than x. And That was a lot in there. But at the end of it all, we got that 2 over x is less than the square root of 2 is less than x. Okay, so I got an interval around my square root of 2. And so time I get a new upper endpoint for my interval chosen for x, I can cook up a new lower endpoint. And I can also get a better approximation, right? But if I take the average of the lower bound and the upper bound, which is 1/2 of 2x plus x, that will also be between the endpoints. And so I'm going to say, right now. Okay, because this will give me an opportunity to get if I have an approximation x, I can always get a better approximation. And so now let's take a look to see how this new approximation relates to square root of x. Okay, I keep saying square root of x, the square root of 2. So let's square it. The square of the new approximation will be 1/4 4 over x plus 4 plus x squared. Now, how does this compare to 2? Okay, well, I take the difference, okay, and the difference using this formula will give me that this right here on the right hand side is a perfect square. It's this square. So the new approximation squared minus 2 is a positive number because it's a perfect square. And so from this it will follow that if x is approximation from above, our new approximation is an overestimate of the square root of 2. It'll be above the square root of 2. So I can let it be my new upper endpoint. I can define a sequence of bn's which approximate from above. I'll let b0 equal 2, and then I'll let any new approximation, bn plus 1, be 1/2 of 2 over the previous approximation plus the previous approximation. And that'll be my bn's, and I can approximate from below by my an, which will be 2 over bn. Okay, so I will have my square root of 2 trapped between my an's and my bn's for every n. Okay, now I can take the difference between these two, and I'll run quick through the calculation here. Bn plus 1 minus an plus 1 is less than bn plus 1 minus an, because an is not as big as an plus 1. And then I substitute in the formula for bn plus 1 in terms of b. I can, my 2 over bn is actually an an. I subtract this an from it. If you do the math on it, we get 1/2 bn minus an. So when I get my new approximating interval around the square root of 2, it's half as long as my former approximating interval, and so each time we just split the difference. Okay, and so in terms of our approximation, we can run through this, and this top table you can do by hand or on a calculator, but you will only have a difference in the looks like the 6th decimal place if you do 3 iterations on this. This is a good way of approximating the square root of 2, and so our real numbers are going to be approximates, be intervals approximating the intervals of rational numbers, an upper bound and a lower bound. And we'll talk more about this in our next lecture.